Hey everyone, in this video we're going to cover Goodness of Fit, section 11.1, which is a really cool section because in this section we get to work with multiple proportions. So far we've done when you do hypothesis testing for one proportion, and then when you have two samples, and so you have two proportions. So in this case, we're going to work with multiple proportions. And so this is what we consider a multinomial experiment. And we know we're used to the binomial experiment. Recall that a binomial experiment has only two possible outcomes. A multinomial experiment is the probability experiment consists of a fixed number of independent trials in which there are more than two possible outcomes for each trial. So think back to when we did the M&M study, and we had the 6 different colors of M&Ms, right? You have brown, orange, red, yellow, green, and blue. Did I miss one? And then when we were doing one proportion, we just kind of focused on, okay, let's look at the proportion of blue M&Ms. Well, in this section, we get to study really all of them at once from the same sample. So the same bag of M&Ms, we can now look at all the different proportions of candies of the different colors, not just focusing on one. So in this section, we're going to learn tools to deal with multiple categories. And it is what we call a goodness of fit test. So the goodness of fit test is used to test hypotheses that an observed frequency distribution fits or conforms to some claimed distribution. So by goodness of fit, we mean that sample data consisting of observed frequency counts for each of the different categories agree with some particular distribution, usually normal or uniform. And those are the ones that get considered most often. So what we are going to use will be the chi-square goodness of fit test. So we're going to be making use of our chi-square table again. We used that when we were doing two proportions. So we're going to test whether a frequency distribution fits an expected distribution, normal or uniform. The null hypothesis that states that the frequency distribution fits an expected distribution, and then the alternative hypothesis is that it does not. So still, the null hypotheses are equals, and the alternative hypothesis are not equals, right? It differs. So the goodness of fit requirements are that our data has to be randomly selected. The sample data consists of frequency counts for each of the different categories. And for each category, we have that the expected frequency is at least 5, and then the observed frequency has to also at least be 5. So this is essentially step 3, is making sure that our sample fits the central limit theorem. And we can use theoretical approaches. We can use the chi-square distribution. So essentially, right, if we have, what that means is that if we have large enough samples, then we can use a particular distribution. So in this case, chi-square. For other stuff that we've done, the t-square, or not the t-square, the t distribution or the normal distribution, the z-scores. Right, so those are different distributions. So we have to make sure that the central limit theorem applies. So in this case, the expected and the observed have to be at least 5. If those conditions are satisfied, then the sampling distribution for the goodness of fit can be approximated by the chi-square distribution with k minus 1 degrees of freedom. And in this case, k is the number of categories. So when we use the t distribution, t-scores, we use n minus 1 degrees of freedom, where n is the number in the sample. But here we're using k, where k is the number of categories. So thinking back to that M&M sample, there are 6 colors, so our k will be 6, so our degrees of freedom will be 5. And then the hypotheses, the null hypothesis is that the frequency counts agree with the claimed distribution, and the alternative is they do not agree. And then our test statistic for the chi-square goodness of fit is we're going to have, this is always a right tail test, and it's the sum of the difference, the observed, so the O stands for observed and E for expected. So you're going to look at what was observed in the sample, what was expected. The expected is usually the claim. And then square those differences divided by E. So we're kind of getting a percentage of the difference, and then we sum all of those. If the expected frequencies are all equal, so if somebody claims, oh, the percentage of M&Ms for every color is the same, then we will calculate the number of M&Ms in the bag, so the total number in the sample, and divided by the number of categories, so that each category has the same number, and thus we will get the same percentage. If they're not the same, then we calculate the expected by doing n, so the number in the sample, times p, the proportion, the percentage of what the expected is. And then this is kind of the usual, how do we decide what to do, right? So critical region, does our test statistic lie in the rejection region or not? So the shaded green, highlighted green is the rejection region. So if we have a large chi-square, meaning it will be in the rejection region, then we reject the null hypothesis. If we have a chi-square that does not land in the rejection region, then we fail to reject the null hypothesis. And so we have a good fit with the assumed distribution. And so the other one would be, if we reject the null, we do not have a good fit. So let's try this example. A retail trade association claims that the tax preparation methods of adults are distributed as shown in the table below. So here's the distribution of tax preparation methods. A tax preparation company randomly selects 300 adults and asks them how they prepare their taxes. The results are shown. So these are distributed results by an independent tax preparation company. Right? So there's a retail trade association that claims these are the percentages of tax preparation methods used by adults, and then a tax company said, okay, let's survey people and see what they do. And so these are then the expected percentages. Notice they are not all the same. So going back to this, right, the expected are not all the same. So we're going to use the expected frequencies would be calculated by doing n times p. So part A, find the observed frequency and the expected frequency for each tax preparation method. And then B, at the 0.01 level of significance, test the association's claim. So the trade association is claiming that these are the percentages. So based on our sample results, we're going to see how close we are. Can we say yes, the trade association is correct and we can claim those, or no, they differ from that? So let's first do part A. Part A, find the observed frequency and the expected frequency for each tax preparation method. So the observed, we already have that. We can just copy that. 60, 43, 117, 29, 51. These are the different methods, right? The distribution, the tax preparation method, is people use an accountant, 24% by hand. So you do them on your own, 20%, and by filling out the forms, right, all by hand. Computer software, so that's like TurboTax or something else, 35%. And then friend or family, 6%, or a tax preparation service, 15%. So I'm just going to copy this and our survey results into a new table and then do the expected. And for the expected, we're going to do, again, this. The expected, because we're saying they're not all the same, the claim is that they're the specified percentages, we're going to be n times p. So in this case, n is 300. So for the accountant, right, it will be 300 times 24%. So 0.24 times 300 will give us 72. And then by hand, 20%, so 0.20 times 300, and so on. Computer software, 0.35 times 300. So here's our table. We have the percent of people, the observed frequency, and now here's the expected, n times p. And so we do the n, it's always 300 times p, the percent in decimal point, and so those are our expected. And so this, you can kind of see then, oh, they differ, right? 60 and 72, 43 to 60, 117, 105. And so now we want to do at the 0.01 level of significance, test the association's claim. And so the steps performing a chi-square goodness of fit test is verify that the observed frequencies were from a random sample, and each expected frequency is at least 5. So going back to the problem, it says a tax preparation company randomly selects 300 adults. Okay, so we have a random sample. Each of the categories has at least 5, so we're good there. So we have verify 1 and 2. Identify the claim, state the null and alternative hypotheses. Specify the level of significance. We know that's at the 0.01 level. Identify your degrees of freedom. And then we're going to determine the critical value using table A4 from our textbook. Let me highlight that and let me pull that up as well. So our hypothesis is the null hypothesis that proportions agree with the claim distribution. So here we could try to say that PA for accountant equals 0.24, and then P was another one by hand, so PH maybe equals 0.20. And then P computer software, so P computer equals 0.35. But notice that this is just kind of long notation. So if you have more categories, it's going to get pretty complicated. And then saying they do not agree, then you have to state all of them like it does not equal, does not equal. So it's a little bit easier to say the proportions agree with the claim and then saying the proportions do not agree with the claim. Or if we were claiming that they were equal, the proportions are all equal or the proportions are not all equal. So in this case, it's better to just write it in words rather than try to figure out all the different proportions. But you can, and just for clarity, I'm gonna write them out, right? So then proportion of friend or family, in this case would be 6%, so 0.06, and then the proportion of tax preparation service would be 0.15. And then for the alternative would be these not equal, not equal, not equal, and so on. Our degrees of freedom will be the number of categories minus 1. We have 5 categories, and so minus 1 is 4. And so let's find, it says, so we have all those things now. So determine the critical value and determine the rejection region. So our critical value we have is it's going to be based on degrees of freedom, so 4, and our significance level. So let's go to our textbook and find it. So from your textbook, when you open the ebook, and if you have the physical copy, just go to the tables. But when you're on the ebook, we're going to go to the table of contents and then go to Appendix A, all the tables. And we're looking for table A4. We can close the table of contents now and then go to the bottom or where I can select my place to scroll, and I want A4. So there's A2, A3, A4. We're looking for the chi-square distribution. And so we're looking at degrees of freedom 4 and 0.01 level of significance. Our level of significance are up here. So we're looking at 0.01. So the one right before the last column. And degrees of freedom are 4. So 13.277. So that's our critical value, 13.277. So let's remember that. And so back over here on my notebook, we're going to draw. So the chi-square is a right tail distribution. I'm trying to make that a little more straight. And so we have something like that. So this is going to be our chi-square. So what we just found is that our critical region, the critical value was 13.2, or was it 0.227? Or was it 0.277? Let's take a look. So degrees of freedom 4, 13.277. So let's go back to that. So fix that, 13.277. And so this here is our rejection region. And so the significance level, right, or alpha is 0.01. So that means that's the area. So that's the shaded area is 0.01. So now we need to find our test statistic. So what we just found is that our chi-square, and I usually call it C for critical value. And this is from the table. And this is 13.277. Now what we want to find is our chi-square S. So this is our statistic. So this is going to come from our sample. So I'm going to do the calculations for this and then see where it lies. Is it placed in the rejection region or does it fall out of the rejection region? And going back to the notes, we had this graphic up here, right? So this is what I'm looking for. Where does my statistic fall? Is it in the rejection region or outside the rejection region? And so our statistic is this guy. So let's compute it all. So I already have my observed, I have my expected, so I can now complete my observed for the statistics. So we're going to do these by hand. So I already filled out, right, our observed, our expected. So when you do O minus E, so that's our -12, -17. So that's the difference, and then you square it. Now our statistic, the formula is that we do the sum of the squares divided by the expected. And so, where did I have it? Right here. So I'm going to copy this over to the notebook so we can do it by hand and do the calculations. All right, so now that I have my same table here, so we're going to have our statistics, so our chi-square, I'm going to call it S just for statistic, is going to be the sum of, right, the formula is the chi-square or statistic is the sum of O minus E, the observed minus the expected square over the expected. I already calculated this quantity, O minus E squared, so that's those are my O minus E squares. So I just need to add them up and divide by the expected of each. So this is the expected for the first one, so 72. So I'm going to have the O minus E squared is 144. So this is 144 over 72 plus the 289 over the next expected, which is 60, plus 144, the next O minus E, right, observed minus expected square, divided by the expected, which was 105. And then plus 121 over 18, plus 36 over 45. Let's just double check. So it's my O minus E squared, so that's the numerators, and then the denominators are all the expected. So 72, 60, 105, 18, and 45. So that's good. And then add these up and see what we get. No need to get a common denominator, just put it in your calculator. So what I got is 15.710. So that was my statistic. Now, if you just want to do it straight up from here without having to do the steps that I did in this table, you can, right? So it would be chi-square equals, and just do it all at once. So you would say O minus E, so 60 minus 72 squared, and then over 72, plus the next one, O minus E, so 43 minus 60 squared over the expected 60, plus, and then the third one, observe minus expected, so 117 minus 105 squared over the expected 105 plus, and just do them all like that. So you don't have to do the work that I did here and separating it. Your book does that, so I just wanted to show you what they were doing, but you can also just do it all in one simple step if you're doing it by hand. So that's our statistic, 15.71. So where does it fall within the the critical region. So let's go back over here where I had drawn the critical region. So our critical value is 13.277, and we just found the test statistic to be 15.710. This is larger than our critical value, so it's going to be somewhere over here, 15.710. So it falls in the rejection region. So that means we will reject the null hypothesis. And the null hypothesis is that the proportions fall within the claims of the association, right? So we reject that. So we will say it's more the alternative that's happening. The proportions do not fall within the claims of the association. So that's how we will do this, and then by hand. Now, the only thing about doing this by hand is that, well, it's a lot of work involved, but also we don't get a p-value, right? The table does not give us a p-value. It only gives us a critical value, and we have to draw the rejection region on our own. So we can go to StatCrunch and try to get our p-value. So how do I do that? Well, so let me put in here observed and expected, and we can copy and paste our data in here. So from our table, so I just go to I'm just going to copy the observed and go back to StatCrunch and paste it there, and do the same thing with the expected. Or, we only have 6 categories, so we can just enter them by hand as well. But I'm just copying and pasting. So now let's go to our notes. And the notes here tell us the StatCrunch instructions. Click Stat in the top menu, select Goodness of Fit from the drop-down menu. So our stat menu is really where we live, right? That's our bread and butter for this class. If you have one proportion, T-stat, C-stat, correlation and regression, this is what we use, the stat menu. So goodness of fit, then chi-square test from the submenu. And then we're going to select or observe frequencies. And then this is number 4 is kind of important, because we're going to select the column that contains our expected frequencies if they're not the same. If they are the same, we're just going to click that they're all the same, and then we're going to hit compute. So it's better if we just do it. So let's go for it. So I'm going to go to what it is, a stat, and we're going to go to goodness of fit and chi-square. And so here's our menu. And so select column, observe, this observe, our expected, I labeled it as expected, so I'm all good there. No, so notice now if the claim was that they were all the same, then we will click all cells are equal. But here we have an expected column, they're not all the same, and then just click compute, and we get our results. And so notice that it gives us the table just to make sure everything is entered the same, right? So this is all good. And notice there's our statistic, 15.71. This is what we calculated by hand. It gives us our N. There are 300 adults that were surveyed. Our degrees of freedom was 4. And the reason we're doing StatCrunch is for p-value. So 0.0034 is our p-value. So let's go back to our notes over here. So we already knew that we rejected the null hypothesis just by drawing the critical region. But now we can also say that p-value was 0.0034, and our alpha, the significance level, is 0.01. So which one is smaller? Notice that our p-value is smaller than alpha. So that means we reject the null hypothesis, which makes sense, right? Because our alpha is the shaded area. So in the critical region, the 0.01 is the shaded area. So if our critical, or if our statistics falls further from our critical value, then when I shade the area from the statistic on, this area is going to be smaller than the critical value, the significance level area. So that totally makes sense. right? So then, because our critical value is so large, our area that it shades will be small. If I had a critical value that was over here, for example, now that area will be much larger than the significance area. So I'm just kind of drawing those correlations there, those associations, I should say. All right, so we reject the null hypothesis that the trade association was claiming that people use. What was the claim? Let me go back to the problem. It said a retail trade association claims that the tax preparation methods of adults follow this distribution. So now we can say at the 1% level of significance, we have enough evidence to reject this claim. And the preparation methods of adults do not follow that distribution, right? So then that's how you would explain it in the context of the problem. Okay, so the next example is the one with M&Ms. So a researcher claims that the number of different color candies in bags of dark chocolate M&Ms is uniformly distributed, meaning they're all the same. To test this claim, you randomly select a bag that contains 500 dark chocolate M&Ms. The results are shown below. So you can do this by hand as well by doing, so this will be the observed, and then we will create a column for the expected. And the expected, right now we're saying that they're all the same. So how do we find the expected? The expected will be, where did I write it? It was up here. So the expected, because we're claiming that they're all equal, then what we say is N over K. So the number of subjects or sample data values over the number of categories. So for this example, we're saying there are 500 M&Ms and 1, 2, 3, 4, 5, 6 categories. So the expected will be 500 divided by 6. And that will give us, what is it? So whatever that is. So that will be our expected. And we can also do this in StatCrunch. So let's go back to StatCrunch and put the data in. Maybe. So let me close this out, and I could delete those, or I can just go data and then load a new window, so a new data table, and then it just gives me a new. And so I'm just going to label that observed, and then put in the values. So here, I don't think I made it available for copy and paste, so we'll just have to enter them as we go, try to remember. So 80, 95, 88. All right, I managed to remember them enough to enter them in StatCrunch. So these are our observed. I don't need an expected because we're claiming that they're all the same. So let's go to Stat, and I'm going to go to Goodness of Fit, chi-square. And we select our column for observed. And now we don't select a column for expected because the claim is that they're all the same. So we're going to say all equal and compute. And so notice that it gives us the chi-squared statistics at 3.06. So this is a very small chi-square. And we can find our critical value by looking at the example. So as alpha is 0.1, and our degrees of freedom, there are 6 categories, so 6 minus 1 will be 5. So when we go to our table, degrees of freedom will be 5, and 0.1 is right here. So 9.236 is our critical value. And so notice that with StatCrunch, our critical value is smaller than that. So we're going to then fail to reject the null. And then notice the p-value, 0.6975, almost 0.7, is much larger than the significance level of 0.1. So we will fail to reject the null. So in this case, we can say, what can you conclude? Well, this researcher's claim is wrong. The or is correct, sorry, because he claims that the number of different color candies at M&M is uniformly distributed, and we just showed that, yes, the p-value is large, so we fail to reject the null. So the null is the researchers claim that they're all the same, and so we can't reject that. So we say, yes, the researcher, there's a 0.1 or 10% level of significance chance that the researcher is correct. Okay, so that's how you do a goodness of fit. So the main thing is that it's based on categories. Your degrees of freedom is based on categories rather than the size of the sample. All right, email me if you have any questions or if you'd like to see more written out work for this one.